Have you ever been in an elevator, going up floor after floor, and had that tiny thought, what is actually holding all this up? It's so smooth, it almost feels like magic. Well, it's not magic, it's physics. And today, we're going to pull back the curtain on one of the coolest secrets in engineering.
So let's just get right to it, because this is the big question. I mean, think about it. Steel rope on a smooth steel pulley. That sounds incredibly slippery, right? You'd imagine you need some giant toothy gears or massive clamps. But nope. Modern elevators use something much, much smarter. Pure, simple grip. Or as the pros call it, traction. And the secret to that unbelievable grip? It doesn't come from some fancy new material or just brute strength. It's actually hidden in plain sight, engineered right into the path the ropes take. That's right, geometry. The safety, the smoothness, the efficiency of the entire system, it all comes down to one single, elegant principle of shapes and angles. It's this one idea that turns a simple rope and wheel into a machine that can lift tons without breaking a sweat. And that brings us to the hero of our story today. It's an engineering term that sounds simple, but its impact is absolutely massive. So let's meet the traction angle, or as it's more commonly known, the alpha angle. Okay, so what in the world is the alpha angle? It's actually super simple. It's just a way of measuring how much the rope hugs the main pulley. That's it. It's not about how tight the rope is pulled. It's all about how much of the rope is physically touching the pulley surface at any given moment.
You can actually feel this yourself. Imagine trying to hold a heavy weight with a rope that's just slung over a tree branch. It's tough. But what happens if you wrap that same rope around the branch one full time, or even twice? Whoa, the friction goes through the roof. Suddenly you can hold way more weight with the exact same amount of effort. That extra wrap, that's the alpha angle in action.
Okay, I know, a formula. But don't worry, you don't need to solve anything. Just look at where our hero, that little alpha symbol, is. See it? It's up in the exponent. And if you remember one thing from high school math, it's that when something's in the exponent, it has a massive impact. This means adding a little more wrap doesn't just add a little more grip, it multiplies it. The power increases exponentially. This is the secret sauce. So, if a bigger wrap angle is the goal, how do engineers actually get it? Well, they design different layouts for the ropes, what they call roping systems, specifically to maximize that hug between the rope and the pulley. Let's check them out. You're basically looking at the two main ways to do it. On the left, you've got the one-to-one system. Super simple, super direct. The rope goes from the elevator car, up and over the main pulley, and straight down to the counterweight. But then look at the two-to-one system on the right. It's got more loops, more pulleys. It looks way more complicated. So why bother? You guessed it, it all comes back to alpha. Now, in that simple one-to-one system, the rope just kind of drapes over the top half of a pulley. It's like a half hug. This gives you a pretty good alpha angle of about 180 degrees. It totally works, and you see it a lot in really high-speed elevators. But that clever 2-to-1 system, with all those extra loops, it forces the rope to wrap all the way around the main pulley. We're talking a full 360-degree hug. It literally doubles the alpha angle. And remember that formula? Doubling the alpha doesn't just double the grip, it makes it grow exponentially. It's a massive difference in holding power. So, we've got way more grip. Awesome. That's obviously great for, not slipping. But the benefits don't stop there. Maximizing that alpha angle creates this amazing cascade of positive effects that makes the entire elevator better in pretty much every way. Well, first, safety, of course. More grip is always safer. But here's the really cool part. Because the geometry is doing all the hard work, the system doesn't have to strain. That means way less wear and tear on the ropes and pulleys, so they last longer. The motor can run more efficiently, which saves energy, and for us, the passengers, all of that adds up to a ride that's noticeably smoother and a whole lot quieter. And this is where the rubber, or steel, meets the road. To get enough grip with a small alpha angle, you have to cut these sharp, V-shaped grooves into the pulley that literally pinch the rope. It works, but man, it just chews up the ropes over time. But with a high alpha angle, you've got grip to spare. You can use these gentle, rounded, U-shaped grooves that just cradle the rope. Less wear, better efficiency, and a ride that feels like it's floating on air. So you can see, getting that perfect high alpha angle is more than just picking a design from a textbook. It's about executing that design perfectly in the real world.
And that takes some serious skill and mastery.
Because, let's be real, nothing in the real world is perfect. An elevator machine room might be cramped. There could be tiny imperfections in the manufacturing of a part, or a pulley could be misaligned by just a millimeter. Any of those things can chip away at your precious alpha angle. Making sure the design on paper becomes the reality in the shaft, that's where true expertise shines.
And that really is the main takeaway here. The experts at Elevator, whose research was the whole basis for this explainer, put it perfectly. They said that chasing the perfect alpha isn't just a technical exercise. It's a commitment. It's a promise to build a system that's not only functional, but is fundamentally safer, more efficient, and designed to last for a very long time.
So the next time you step inside an elevator, as the doors close and you start to rise, maybe you'll think about it. You're not just riding in a box on a rope. You're being held perfectly and securely by an invisible geometric hug. The simple, elegant, and incredibly powerful grip of the alpha angle.